Hello, welcome to the final week. How exciting! Even better, there's only one lecture to go. It's going to be about environmental effects of mining operations. So we're nearly there. Well done. The light is well and truly in sight. We'll rapidly moving towards the end of a trimester and for some of you the end of your degree, which is fantastic. Okay, so environmental issues, obviously a very important aspect of geological resources, of mining. There is important responsibilities in place for mining practices to reduce environmental disturbances and to rehabilitate. We don't want to negatively impact the environment, and we want to do mining in a sustainable way. So in this lecture, we're going to talk about a few of the key environmental issues and some of the ways that they can be managed and how this relates to specific deposits. But obviously, it's a very complicated issue with local specifics, as well as wider implications. And this is only touching on the environmental issues. There's cultural stuff that I know a lot of people mentioned in their talks, which is fantastic to be aware of as well, and social impacts that mining has, both in positive and negative sense. So just be aware of those. And it's also a good time to remind you that there is a course for environmental geology in third year. So be wary to take those, and you can go into a bit more detail about these sort of processes. Okay, so mining practices with the sort of self-obvious aspect to begin with. It involves removal of material from its environment. And this can be done via a variety of methods: open cut, underground, in situ leaching, and within those classifications there's variations in the style of mining. Could be stoping or longwall, etc. So a lot of you have touched on this already about how you decided to best pillage your deposit from the New England. So you're well on top of the best way to do it, cheapest ways, etc. So no matter what the process is, we're going to have an environmental disturbance. So it's about trying to minimize that, mitigate it, and broadly move towards a sustainable practice. So how can we do that? So here's just an example of a big open cut from Cobar. In this case, quite a substantial hole for copper gold in this case. So we're initially removing the topsoil and the vegetation. That area is denuded of material. And in the past, historic mines, which I'll touch on in a bit later, Broken Hill, they denuded huge proportions of the landscape of trees for wood, for the underground workings, as well as for, fires, for smelting, or for running steam wheels and things like that to run the whole mining practice. So there's a wider influence beyond just the actual hole in the ground to be wary of. So on top of that, we will then start to remove regolith and then the rock, which includes blasting and drilling, etc., to get down to deeper into the ore body. And sometimes this involves overburden that's just moved to waste. And then we're into the main ore envelope, in which case we will then have to try and separate ore from gangue that we might put in a stockpile. At the back here might be some stockpiles. Then the material, the ore, is treated through a processing plant, and the product, the concentrate is taken away, and the leftover from that is what we call tailings, and that's usually pushed into tailings dams or other sort of stockpiles. So quite a big footprint in terms of the mine site for open cut. Underground, as in terms of a visual eyesore, is less prevalent. Here's an example from the Plutonic mine in Western Australia for gold. It mostly involves blasting and drilling, removal of rock again, stockpiling ore and tailings. So it's variation on a theme. We might have less overburden or gang to remove, but we are presented with different issues, including health hazards and safety issues about underground mining. Here's some bolting here to stop wedges falling out of the roof. So we can go to another example, coal mining, for people that move through the Hunter Valley in New South Wales. You'll be very, very substantial pits for coal mining. And we have these large sleeves that commonly are mined by longwall mining now. And so we can have a similar style to an open pit. And we might be looking at less metallurgical processing, but still a prominent footprint. Another kind might be alluvial workings. Here's the Shotover River in New Zealand near Queenstown. We've got barges and picking up of aggregate. So we're disturbing the soil and the vegetation. There's limited vegetation here. We could be influencing the nature of the river and its behaviour, so it might change its pattern, it might reduce its energy, which then have wider knock-on effects to the ecosystem that we have to be wary of. Okay, so that's just the physical footprint. So we have to be wary of what the products are and what the end manifestation of the environment we're left with after that mining. An additional aspect is aspects of processing. So we dig up this ore, then we have to concentrate it. So it involves a variety of methods from primary and secondary metallurgy. So we'll start with things like crushing and grinding to concentrate the ore. We might use gravity separators. We then might add chemicals to extract the metal product, and in which case we're creating a variety of contaminated waste byproduct. Here's an example of froth flotation at Browns Creek. This was a method designed in Broken Hill to agitate the ore body and concentrate, and then it creates bubbles which take away certain sulfide minerals and products. And so depending on the nature of the ore influences our processing method. And the nature of the ore body means that the waste product can be of highly variable nature. So some mines, it might be a big issue. Others might be contaminated in certain heavy metals or lead to acid mine drainage and things like this that can cause additional environmental concerns from the product, as well as how it's treated, what chemical reagents we use, and how they might behave in the environment. So this is where water comes in. It is vital to mining. They need lots of water. It's used to treat oil, used to treat ore. It has chemical additives to promote metal extraction from minerals. We create large tailing dams that may have impact onto surrounding waterways. So water quality becomes a very important aspect of mining processes. So here's another influence of processing, cyanide leaching at Peak Hill. So cyanide is commonly used to help liberate gold. So we might use broad-scale processing of ore dumps and put it through leaching process to liberate that gold. Although it sounds bad, typically the cyanide is evaporated and has limited downfield environmental issues, but this is not particularly a overly attractive scenario, and we don't want things to go wrong. So we have to be wary of what processes are happening to do them in a safe and sustainable manner. So on top of this, one of the biggest issues is when things are actively being mined. In many ways, there's a direct consequence there of the mining company to be aware of their environmental obligations. Whether they follow through on that is a different story, and whether they've set aside enough money to do that is also a different issue, but that is increasingly tried to be legislated to make for better outcomes. So it enables, in an active mine, at least some degree of responsibility, in an ideal world, to be placed on that mining company. But we have many mines that are abandoned, old, and were possibly done in eras where rehabilitation wasn't even considered, or the company might have fallen over and ran out of money and never fulfilled its rehabilitation obligations. And these can cause significant but localized contamination of the environment. And we have aspects of our state governments that are meant to look into mine rehabilitation to try and reduce these issues, but we're left with infrastructure. This is the case from South Australia, Radium Hill, in abandoned sort of mine settings, and we might have issues about how their processing or environmental degradation has been addressed. So, what sort of environmental effects are we talking about? So, the obvious one is damage to land. We might have a big hole. We might have denuded landscape. So we might need to focus on rehabilitation in terms of reforming an ecosystem or filling in holes and etc. So there's those sort of direct aspects. We additionally might be releasing toxic substances, so we might be bringing up material that is in higher concentrations to the surface, and we might be reacting that with a variety of chemicals that can cause issues. A nice case of this might be something like Broken Hill, where we have substantial lead ore brought to the surface and ground down and creates a dust that can then spread through the town via prevailing winds, and we might have elevated lead concentrations in children around Broken Hill, and Mount Isa is much the same. So, that's a consequence of us bringing the ore material to the surface and having it exposed. So we need to be wary about how we might mitigate that, whereas previously when the ore body was in the ground, that issue was much more minimal. Acid mine drainage, I'll talk about that in a bit more depth a bit later. We have a variety of other health and safety issues about, could be things like asbestos dust, or just broader holes in the ground. So there's diverse issues there. We have noise pollution, trucks, and visual pollution. People don't necessarily want to look at denuded and mine landscapes. And we also have issues surrounding the legislation of sustainable mining or mine rehabilitation, and who affords the cost and how that is administered. As we've discussed at different times, many cases there's a reneging of the costs, or the company goes under, and these rehabilitation aspects are avoided, which is not a favourable situation. And mining companies need to be aware of their social license, that people don't want to see broad-scale environmental degradation. Okay, so damage to land, we have open cut, we have underground. So open cut on the surface is much more prominent, but underground mining causes substantial issues, especially if we have collapses. We have tailing dams, so where we've that product of the concentration. We have waste dumps, we have other infrastructure, we might get contaminated waterways, and we have old roads and airstrips potentially denuded for that mining practice. So here's just an example. This is Plutonic gold mine. Here we have what look like substantial tailing mines. Here's the actual open pit, probably progresses into an underground hole. There's a few other open pits here. We have prominent roads and other mine infrastructure around. So the footprint can be quite large, despite an ore body being a fairly focused component that we need to be wary of, and there's variability in where the stream drainage is going, potentially out of tailing systems where we can produce acid mine drainage and etc., depending on the deposit type. So what sort of toxic substance are we talking about? We might have chemicals like such as cyanide or other chemical reagents to liberate ore. We get waste products, so waste rock is barren, it's low grade. We might get tailings, so concentrated, so sometimes they might have heavy metals content in them that could be liberated by water. We also might get slag if we were smelting on site. Dust pollution from blasting and disaggregating the rock, as I discussed, places like Broken Hill, this could be an issue if it's substantial lead concentration. Commonly the waste product is used for the infrastructures, so it's moved around, and whether that is ideal or makes it difficult to rehabilitate the area. There's limited topsoil for planting of trees that might not have been, or other plants that should be native to the area. We might get aerosol released from roasting and smelting processes. The big chimneys are pulling out chemicals, pollutants into the ecosystem, and we might also have leachate from tailing dams and processing sites. So a variety of aspects to the environmental degradation. Here's just an example of slag, beautiful textures here. This is just the byproduct of smelting some ore, commonly copper's iron sulfides, and we're left with an iron product, an iron silicate product called slag or pig iron, and it's quite prominent in many old mine sites where smelting was an active processing method. Here's an example of a waste rock. This is Collison's silver deposit up near the Mole Granite in New England area. The main shaft is behind us, and we have these prominent piles of sulfide waste rock, which actually surprisingly is still fairly high grade in things like silver and potentially indium, strewn across the landscape. And subsequently, I was up here not so long ago, they've actually, the Department of Mine Rehabilitation has actually spread out this waste rock, and so it was just this big denuded area, no topsoil, prominent waste rock, so it's not actually a favourable rehabilitation outcome, and so there's a lot to be done to bring back these setting to what it might have looked like with all these prominent trees, etc., as we can see in the distance. Here's an example from a coal mine, much bigger footprint to the previous example, huge piles of waste rock. So, how do we infill this area? What do we infill it with? How do we rehabilitate this site back to what it should look like? So smelting and processing, this is Queenstown in Tasmania. We've got a prominent smelter stack. If you go around the area, it's highly denuded for historical mining, and you see a common smudge of material throughout related to the smelting. So we also have examples, here's another example, prominent stacks, pollutants, and we can see broader environmental issues in places like Broken Hill. You can actually identify isotopes from the start of mining at Broken Hill in the Antarctic ice cores based on lead. Waste rock, so this is at Bakers Creek, so Hillgrove. We have underground workings and material that's dumped out into the river, and then it can potentially cause higher concentrations of particular heavy metals that may disrupt that ecosystem or flow further downstream. Tailings. Here's an example of a big tailings dam. They've used the sort of waste products from the mining to dump out into an area and form a prominent basin for their water storage. And this material is disaggregated, and it could be concentrated in particular sulfides, which can lead to acid mine drainage, or other heavy metals, which can cause problems when we're leaching out. So here's some more examples of tailings. It's been eroded by water and wind. It's very fine, commonly very fine material. It's easy to transport. This is tailings layers. It forms essentially a new sedimentary rock, very fine, and it breaks down and starts moving through the environment, which is less than ideal. Here we example, it's forming like a sort of a siltstone, compacted. We have essentially stratigraphic layers of history of tailings, and this is a sort of material that is ground up waste rock and forms these dams. Here's some nice examples. Prominent layers can be hard, but can also be still unconsolidated and move further down the waterways and carry with it broken up material, potentially heavy metals, but it's also disaggregated a lot of sulfides, so it enables a prominent surface area for things like acid mine drainage. Here's some examples of revegetation. Here's the tailings. We're starting to get revegetation, but depending in the Hillgrove example, this could have high arsenic content and makes it hard to revegetate the right sort of ecosystems, and we have to have specific plants to use and to consider when we try to rehabilitate tailing sites. So here's another example. This is Gulf Creek. We have highly oxidized sulfides from a massive sulfide deposit, prominent scarring of the landscape, precipitation of iron oxides related to the processing and exposure of prominent ore bodies. This may then lead to sulfide production as it's oxidized the ore, and we get efflorescence. Here's a prominent example. Sulfide ore is a good indication of sulfide occurrence, much like we see in geothermal systems at the surface. That can be, toxic to many of our native ecosystems. We also start to precipitate iron oxide through these reactions. Here's some nice iron oxide deposits. And then we have to sort of look at what is the broader background contamination of heavy metals as they're brought out of these systems. So here's a graph. This is work done by Paul Ashley. We have log arsenic, log antimony, looking at the Hillgrove, Bakers Creek area. So the Hillgrove mine and how it, it's the headwaters to the Macleay River, prominent river in the East Coast. So at the mine, we have substantial concentrations above background, 5 log units for this material. And we have a prominent plume that is, essentially potentially 50 to 100 kilometres downstream of elevated arsenic and antimony concentrations into the Macleay River. And, you might not be getting down to background for 300 kilometres. So we have this prominent contamination into the catchment of heavy metals, which can cause big issues depending on its bioavailability in the environment. And here's just some examples of background concentrations, and we're elevated relative to those. And here's the Halls Peak, Chandler Macleay cross section, looking at zinc, copper, and lead. Again, a less dispersed plume of heavy metal contamination, but reasonably substantial into the background concentrations. 50 above 50, or zinc, 20 copper, and things like this. So it can cause issues downstream. Okay, acid mine drainage. We've heard a lot about this. We've discussed it at various times. It was a very prominent effect of mining. In essence, we dig up sulfides, we expose them at the surface. This might be through waste rock, might be through tailings is a common example. We have water filtering through. We have sulfides at the surface. They oxidize to sulfates. So we have a breakdown in the reaction. So massive sulfides plus water plus oxygen. We end up with liberation of metal, sulfuric acid, with water. And so we're actually producing a acidic water that comes out of this system and potentially liberating heavy metals. So we're producing a acidic water that's rich in heavy metals. So it's very bad aspect to mining, and we need to be wary of how to minimize this. So this is common for certain mines. Not all metalliferous mines produce AMD. So of course, its deposits are usually pyrite rich and contain little buffer acid reactions. So things like skarns are not that bad because they're hosting a lot of carbonate. We have a lot of carbonate waste rock, and if you add limestones to the base of the tailings, you can actually rehabilitate the acid mine drainage by reacting with an alkaline rock and trying to change the pH back towards neutral. Orogenic gold, of course, most of it is gold, limited sulfide, so it's not a bad deposit. Also contains carbonate in the gangue, carbonatites, and Mississippi Valley. And these other ones have limited iron sulfides, kimberlites, Greisen systems. So it's mainly related around your massive sulfide style deposits, ZX, VMS, potentially epithermal gold styles. So how does this work? It's okay, you don't have to remember the geochemistry, but in essence, we have the oxidation of sulfide. So here's pyrite. It's being oxidized with water. We liberate the iron, so we might precipitate iron oxides. And then we have the sulfuric material and hydrogen ions that can change the pH of the system. So then this ion might be oxidized, and then might be catalyzed these systems. We might produce more pyrite, more ferrocyanide from additional pyrite. So it's essentially separating the iron and the sulfur. Sulfur mixes with the oxygen and released hydrogen. So how does this happen? It's the unconstrained weathering of sulfidic mine waste produces the AMD. What happens is we get the local disappearance of aquatic life and vegetation. We get locally confined heavy metal pollution and acidification of streams and soil. These plumes progressively reduce as we move further away. We might get regional pollution of topsoils like arsenic near the mole tablelands. But big question becomes, is it the nature of the bioaccumulation, its bioavailability, and subsequent biomagnification and heavy metals in aquatic algae and terrestrial plants, so mercury and fish and the like. So that's where it becomes an issue, and that's where it has to be explored in detail for site-specific examples. So how do we risk assess this? Potential transfer of the heavy metals into grazing animals. Is this likely to happen? What is the long-term AMD potential? And what are the heavy metal contaminants? And how does this extend and relate to soil quality or water quality guidelines? And so then it's about mitigating and trying to reduce this, which should be done anyway, to avoid substantial contamination. Here's some examples. This is the Ottery arsenic mine near Emmaville in the New England area. Here's an old adit. We have some very ugly looking water piling out of the adit. Here's some old tailings, and again the water is not pleasant. Its pH is less than 3, highly acidic. We see these iron oxides and aluminium oxide precipitates. So this is a prominent example of acid mine drainage, and further along you have an arsenic plume downstream of this system. Here's Baker's Creek at Hillgrove. Look at the colour of that water. It doesn't look pleasant for a swim. We also have seepage from Mary Kathleen over here. So we start to precipitate iron oxides to form these red colours associated to that AMD reaction. We can also do it in the pit. Here's Peak Hill. Substantial acid mine drainage as the water flows through the ore body. And we can also get it out of tailings dams because we've broken up those sulfides. Potentially not what we wanted as an ore. Okay, so other aspects, we have things like health and safety. So this could include safety of mine workers, local residents, so things like working conditions, personal protective equipment, suitable training and equipment, safety inductions, qualifications, appropriate work hours and conditions. Fatigue management is huge in mining. We also have to have things like keeping the mine safe. Many geologists work as engineering geologists to be sure that geological hazards like faulting that could lead to collapses in underground mines or open pits are mitigated and identified. Then we also have impact to the local community, contamination of the mine products, community consultation and communication, cultural aspects, those broader issues that need to be taken into consideration. So dust comes from blasting. We've sort of covered this. Windblown off tailings dams. We're crushing and reducing the size of a lot of material, so it's very easy to be dispersed. We also have dust in the environment. How much watering down of the actual practice of mining is very important, especially, famous cases with asbestos, but also silicosis is a prominent issue. We've discussed this with some people in the tutorials. So these dust-borne diseases need to be well managed and considered. Here's prominent dust. Doesn't look particularly healthy. This is from Escondida in Chile, big copper mine. Here's more dust blowing off tailings dams. Like I said, if they're lead or asbestos, they can cause prominent issues. There's many of us. You might end up as the drill monkey. In this case, it's RC drilling, very dusty work. So important to wear masks and things like that. Noise pollution is prominent, blasting, crushing ore, etc. So many of the old mines that are essentially operating in town, because the town was developed around them, noise is an even bigger problem. Here's examples of the crushing, conveyor belts. So, rehabilitation. What's the natural rehabilitation process? Commonly the best manner to do this. So recolonisation of disturbed areas by plants that accumulate metals. Some examples there, aquatic algae or certain angophores, and they can handle the high metal content, and they are progressively drawing it down. So much so that some people actually want to plant plants to take up the metals and then mine the plants. So, it's gone the next level. So we're decreasing that level of heavy metal contamination and trying to rehabilitate the environment so other plants can then be happy and stable in that system. But, ideally you want to try and do the things that are native to the area. So metal-rich mine waste is to be removed or for processing or sealed by impervious layers so we can reduce water moving through them and leading to heavy metal contamination. So we have to be wary about where the waste rock should go and how can we keep it from being destabilized. Reduce the effects of landslide and erosion, try and rehabilitate material, add topsoil, add vegetation, stop prominent erosion, which leads to more oxidation and potentially more contamination. Construction of wetlands. Wetlands are great filters for contamination. It's partly why they're used in sewage treatment plants. Adding things like lime drains to try and change pH. And revegetation, very important with native plants, and try and bring back the ecosystem. And in many ways, mines are getting better. There's now many things like biocredits that they're utilising. The government's trying to utilise to leverage for them to be more focused on keeping the natural ecosystem there or rehabilitating it. So it's important to remember that every mineral deposit is unique. So it occurs in a specific location. It might be related to different climatic conditions, different rivers, different ore, and they all combine to make every mine a specific case, and to be wary of those when it comes to environmental considerations. But we all have common effects from wastewater, waste rock, ore processing and local land disturbance that we need to be aware of. So if we talk about certain environmental fingerprints of ore deposits, if we have our orthomagmatic So pegmatites, carbonatites, nickel sulfide or chromite, and things like the Bushveld. Little to no problem with AMD, except for nickel sulfide deposits. So most of them don't have sulfides, but we don't have pyrite, which is the main contributor to AMD. Pentlandite, chalcopyrite, pyrrhotite may also be acid generating. And the host rocks might contain significant carbonates, which are natural acid buffers. In terms of processing, minor uses of chemicals, except for nickel sulfides, and the waste product, significant waste rock, but little contamination for most. So we might be more wary about erosion and rehabilitation of the ecosystem. Skarn deposits, negligible AMD. They have low pyrite content and they have buffering host rocks. Processing, significant uses of chemicals for metal extraction, including froth flotation and cyanidation. So that's where we have to be wary of contamination. Late magmatics, so porphyry, grise, and other granite-related deposits. AMD is generally low sulfide deposits, but they do contain pyrite, which is concentrated in the tailings and can lead to AMD. And the host rocks are not buffer acid reaction, so we have potential for AMD that we need to mitigate, maybe with introduction of limestones, and we have potential for heavy metal contamination. And processing, significant use of chemicals, froth flotation and cyanidation. Epithermals, moderate risk to AMD, occurrence of pyrite and lack of acid buffers, significant risk of heavy metal contamination, particularly arsenic, antimony and mercury, and the processing is similar to late magmatics. VMS, high risk of AMD, prominent sulfides, particularly pyrite, poor buffering capacity, potential metal contamination, processing predominantly froth flotation and risk of more contamination. Orogenic gold, low risk because they're minor sulfide and strong buffering potential with the carbonization of host rocks. Heavy metal contamination is the main issue here, particularly arsenic and stibnite. Antimony. Cobalt sulfate, similar to VMS for AMD, and we have processing with cyanidation. SEDEX, very high potential for AMD, significant pyrite, significant risk of heavy metal contamination, processing from froth flotation, carbonate, red bead copper, low AMD, carbonate, low AMD. You start to get an idea. Uranium deposits low to moderate potential depending on the amount of pyrite, possible heavy metal, possible radioactive contamination, and possible contamination of surface materials. So you get a broader idea as each deposit's different. Its circumstances are important, and this influences how environmental mitigation is completed. So it's important to know the ore body, know its surroundings, be wary of these processes, and we need to keep mining operating. Well, we need to force it to operate in a sustainable way where this rehabilitation is taken into account more so than in the past. So just some of the final deposits here, placer, industrial and minerals. Thank you.